Hey, John here, looking at our full adder. Let me zoom in on here. That's right there. Okay, you'll recognize this as a full adder. We have the add ends here, your A and your B inputs. You have a carry in. You have your sum out and your carry out over here. Now, if you wanted to add together two 2-bit numbers, let me see if I can get this all on the screen at once here, right? So here's your A, your least significant bit of A, and the most significant bit of A, least significant bit of B, most significant bit of B here. Again, you have a carry in. Usually the carry in to the least significant bit would be a 0. You have your two sum outputs here, and you can see that the carry out of the least significant bit routed to the carry in of the most significant bit. All right, and of course your carry out and the most significant bit. You can see we could continue this along to other stages of the adder circuit here. Let me see if I can rotate this. Might be easier to see on this screen. Yeah, there you go. This is closer to what we drew up the other day. Okay, so what do we got here? This is a 4-bit binary adder. These are A and B add-ends come in on the top here, the carry in of the least significant bit here, and the 4 output bits for the sum come out here, and we have the carry output of the most significant bit on the far left here. Now, before we get too far, let's review how we add together two 4-bit binary numbers and what happens with these carries and stuff. All right, so we have two options, right? We have unsigned and we have signed. So let's do an unsigned one first. Let's say we want to add together the numbers 10 and 7. What do we do? Well, 10 is what? 1010 in binary. And a 7 is a 0111 in binary. We're dealing with 4-bit numbers here to match our adder that we just saw there. All right, so I want to add these together. What do we got? 0 plus 1 is 1, and there's no carry. 0 plus 1 is what? 0 with a carry. 1 plus 0 plus 1, 0 with a carry. 1 plus 1 plus 0 is 0 with a carry. And we get this carry bit over here, all right? So what do we get here? Well, what we want is 17, right? Now in binary, 1, 2, 4, 8, 16 plus 1 is 17. But remember, we always truncate our sums. So what we ended up with is 1 here. And this is wrong. And remember the rule, when we have unsigned sum, if there's a carry over here, we have overflow. Now, the rule reverses if we're subtracting, but we'll talk about that later. Now, let's look at what happens with a signed add. And just for fun, let's drive a point home here. Let's say we wanted to add together -6 and 7. All right? We know we should get a 1. What do we get? Well, what's -6 in binary? Well, first, let's just calculate it off to the side here. 6 is what? 0110. And it converted into a -6 to get a 2's complement value, right? You flip the bits, and then you add 1, okay? So what we're doing now is we're going to add 1 to this bottom guy. 1 plus 1 is 0 with a carry, and that's 1 with no carry. That's a 0, and that's a 1. All right, so that equals -6 in binary. So we have 1010. Now we're going to add 7 to that. Well, that's 0111. And what do we get? Well, look what's happening here. We're literally adding these same binary values. And all is said and done, if all we do is look at just this and just that, we're doing the same math. And that math will be done in the exact same way. And that's the point here. 0 plus 1 is 1 with no carry. 0 plus 1 is what? 0 with a carry. This is 0 with a carry, 0 with a carry, and we got a 1 over there. Again, we truncate this, and we end up with the answer of 1. Now, this time it worked. Why? Because we have -6 plus 7. We do get 1. All right, so what's the rule here? Remember the rule when we're dealing with signed addition. We look at these 2 bits right here. And we say overflow is if not same. We have an overflow. Okay? quite often overflow is abbreviated to OV here. Okay, so in this case, there is no overflow. And this time we do. So the point here is to reiterate, the concept of overflow is only in the way that you interpret your results, okay? It has nothing to do with the mechanics of adding these binary values, all right? These binary values are added together regardless of whether they're signed or unsigned in the exact same manner. So the beauty here is you can see the full adder working, right? You've got 3 bits in every one of these columns. It turns out the least significant bit always has a carry in of a 0. But the rest of this stuff, it carries forward, right? So you can literally see the full adder with the little carry output next to the sum wrapping around up to the top in these cases, right? Just like our schematic diagram here, you can see the carries coming out of each one of these columns, right? And propagating forward. Again, you've got the A values, the 4 A bits, the add end for the A's, the add end for the B's, your carry in on the least significant bit, we simply set to 0, and this is going to be the circuit that will do the exact math that you just saw me work out on paper. All right, now let's do a quick review on what it means to subtract. And we're going to see whether we're dealing with signed numbers or unsigned numbers. Again, they're just the same, so we won't differentiate anymore in terms of just the subtraction. The way we deal with overflows is different between the two, but we'll get to that in a minute. So how do we subtract? Remember, we take the 1's complement of the subtrahend, and we add 1 to it. So let's say I want to take, in this case, let's take 5 minus 3. We should get 2, right? Well, 5 in a 4-bit binary number is what? 4 plus 1, so that's 0101. And I want to subtract 3 from that. Well, what's 3 in binary, right? 0011. Okay? Now, how do we do this? We take the 1's complement of the subtrahend here, which is 1100, I should have said. And we leave the minuend alone, 0101. And then we add them. And remember, we set the carry in the least significant bit. So this is the flipping of the bits and adding 1. Okay, now we have to do this all at once in order to deal with the overflow situation. And again, we'll come back to that in a minute. So this is why we want to do it this particular way. In other words, you want to add the 1 using this carry in that we've been kind of kicking under the rug otherwise while adding, right? So what do we do now? We take 1 plus 1 is 0 with a carry, right? And that's 1 with no carry, and that's 0 with a carry. What is this? 1 plus 1 is 0 with a carry. All right? What do we get? We actually got a 2 here, didn't we? Okay? So this is 5 plus a negative 3. And we know that's the same as 5 minus 3, right? So we got the right answer, but we have this carry. Remember, we truncate our sums. And remember, the overflow rule for unsigned numbers is that we have overflow when this is 0, okay? Unsigned overflow when this guy right there is 0. Okay, that's called the carry bit, sometimes abbreviated CY. If these were signed binary numbers, and we can't really tell by just looking at them right here, right? Because this has the same value. 5 is 5, whether this is a signed binary or an unsigned binary. And 3 here has the same encoding, whether this is signed or unsigned as well, because the most significant bit is 0. That's one of the benefits of using 2's complement to represent your signed values, because all the positive values of 2's complement numbers are the same bit encoding as the unsigned binary numbers have, right? Okay, so the rule for signed binary numbers during a subtraction that's done this way, it turns out is the same rule if you use this technique for adding. And remember, that says when these things are different, then we have a signed overflow, okay? And in this case, we do not have a signed overflow because they're the same. And we do not have an unsigned overflow because it's not 0. Okay? Again, during subtraction, the unsigned overflow rule changes. During addition and subtraction, the signed overflow rule is the same no matter what. Okay, so again, what did we do here? This addition operation is the exact same thing as we saw when we added, positive numbers. When we were doing adding and other, this operation, the point is always the same no matter what. In order to do a subtraction, we need to take the ones complement, right? This converting the 0011 to the 1100, this is called the ones complement. Okay? And then we have to set the carry on the LSB. Okay? To do a subtraction, this is all we need to do. So let's add an inverter to the subtrahend. Okay? Look what we got here. Let me rotate this like we did before. That worked out pretty good, I think. Yeah, that looks good. So I guess now we can turn our head sideways. How do we do a subtract? You negate one of the operands and then you add them. And the negation, the process of negation, is to do this ones complement, which is just simply put a not gate in there and then set your carry in to a 1. And again, this circuit matches exactly the way we drew it out on paper. Here's your least significant bit, right? Your A's and your B's. Remember, the B is the subtrahend. This is going to be A minus B. The thing that you negate is the thing that's going to be the subtrahend, okay? So we add them, just like before. You see the carry chain going on in here, okay? You got to carry out over here, just like before. So all we need to do is flip the bits on the subtrahend and add 1. So now we have an adder down here and a subtractor. So we can reuse this circuit exactly as it is, as long as we have a way to turn these inverters on and off whenever we want to. And we need to be able to set this carry in accordingly as well. Well, it turns out there is a straightforward way to do exactly that. And that turns out that we can do it like this. Now, let me get a bird's eye view here first. We're going to see these gates over here. This is going to deal with our overflow. We'll talk about that in a minute. But look what's going on here. These 4 boxes in the blue dashed lines are, each one of these is a full adder. And we'll zoom in a minute. You'll see the carry chain going through there. The key is this over here. Notice these are not the NOT gates anymore. We didn't use inverters over here. We're using Xor gates. So let's rotate this around and get a closer view on what's going on in here, all right? So in order to complement the thing, ones complement the B inputs, our subtrahend. Look what's going on here. You can use an Xor gate to do this. So our B inputs, sometimes if we want to do an addition operation, we want to leave this alone. We want B and A to flow into our full adders down here, and you can see the carry chain flowing around through here, right? Just like before. So the part down below is all the same as it was in the last shot. But this one, we replace the NOT gates with these things. Let's see how this thing works. Remember in XOR, if the 2 inputs are ever the same, the output's a 0. Odd parity, right? Whenever the inputs are different, the output's a 1. Again, that's odd parity, okay? Because one of these would be set. So let's say that we have this signal over here called op, and we hook that to one of the inputs of this Xor gate. If op is a 0 here, then this input here, when they're both zeros, this will output a 0. If op is a 0 and the B0 is a 1, then the output will be a 1. So as long as op is 0, B0 will flow through this gate unscathed, right? But if op is a 1 and B0 is a 0, then the output of this gate's a 1. It'll be the opposite of what B0 was. It's a not function at that point. So if op is a 1 and B0 is a 1, now they're both the same. We have even parity. The output's a 0. So what we have here, we're using this Xor gate to calculate the not function only when this op signal is true. So if op is 0, B 0, 1, 2, and 3 flow right through these gates unchanged. If op is ever a 1, we've just done the 1's complement of our input on B. So now we have a programmable circuit here. This 1's complementer, as you can see over here, this is conditional based on this op function. Now, remember, when we want to subtract, we want to set the carry in on the LSB to a 1, right? When we're adding, we want the carry in on our LSB to be a 0. So we take this op function and we connect it to both. When op is a 1, this will flip the bits of B, and it will add 1 to the least significant bit. So now what we have is a programmable circuit here. I don't know how to rotate it back. I guess you got to rotate it around and around. All right. So, and as I've labeled it up here, I got 4 full adders. We've seen that enough already. We've got the carry in down here, and we have the op going to do our conditional 1's complement. So this is a multifunction adder and subtractor kind of a circuit, right? It's programmable. You program it by putting a bit right here. Okay, now let's look at down here. When we add all these numbers together, the adding and subtracting, no matter what we've done, it doesn't matter. The adders are connected. The carries are the same. The part in these in all these blue dashed boxes doesn't change. So let's not worry about that. What do we do when we're done? Okay, so depending on how we interpret the results, let's look at the signed overflow output here. That's what SOV means as I've drawn it here. This Xor gate is connected to the carry out here, and it's also connected to the carry out over here. We say it is comparing the carry into the MSB with the carry that's coming out of the MSB. If the carry in of the MSB is ever equal to the carry out of the MSB, whether they're both zeros or both ones, this will be false. That's exactly what we want. Whenever the carry in equals the carry out of the MSB, we know that this addition, if we're going to interpret the results as a signed number, we will see an overflow if the carry in is not equal to the carry out, whether they're both, a 0-1 or a 1-0. It doesn't matter. As long as they're the same, there is no signed overflow. This gate right here calculates and reports whether a signed overflow has taken place. And again, this only depends on how you're going to use the results later on. So at the same time, we can also calculate whether an unsigned overflow has taken place. Now, when we're adding, remember this: the unsigned overflow is reported by a carry coming out of the MSB that's 1. When we're subtracting, we get an unsigned overflow if the carry coming out of the MSB is a 0. So let's play the game with the Xor gate again. Look at what this other input is doing over here. Comes over here, goes over there. This is also connected to this op over here. So remember, when op is a 0, we're adding. When op is a 1, we are calculating the difference. We're subtracting, okay? So that's what that signal is that comes in down here, okay? So if this is a 0, as we saw before, the carry out over here just goes through this gate and is reported as the unsigned overflow. And when we're adding and we have a carry out of the MSB, then we do have an unsigned overflow. If we're subtracting, this signal here will have a 1 on it, which will cause this gate here, as we just saw, to become an inverter, so to speak, which means if the carry out is 0 during a subtraction, this will become a 1 over here, which is exactly, again, what we want. So we just use these two Xor gates hooked up exactly like this, and it can report whether a signed overflow and or an unsigned overflow has taken place after an addition has completed. Now, I cannot stress enough that those overflows will only work if you add the 1 using the carry in on the least significant bit as shown here. Because if you flip the bits on the subtrahend, then you add 1 to the subtrahend, and then add that to the minuend, you will not get the right answer. Okay? You must do the adding of the 1 and the minuend and the subtrahend all at the same time in order for this to work. All right, so here's a bad example. All right. Okay, in red, so we all realize this is an example of how not to do something. Okay, so what's wrong? Okay, if we decide to flip the bits and add 1, then do the addition. That's what I'm talking about here. Okay, so what happens if we want to subtract 1 minus 8? Okay, now, if this was unsigned, we'd be looking at 1 minus 8. If this was signed, we'd be looking at 1 minus a negative 8, right? So let's naively do this wrong. So what are we going to do? We're going to flip the bits in the subtrahend over here, right? 0, 0, 1. Flip the bits of this, we get 1, 0, 0, 0. Right? No, you don't. You get 0, 1, 1, 1. Now, if you did this right, you would simply do the addition now and you'd put the carry in like this. Okay, this is the right way. Here's the wrong way. Okay. The wrong way would be to add 1 to the subtrahend and then do the addition. Okay, now you can see this is already broken. If I add 1 to this thing, what do I get? I get let's see, 1, 1, 1 plus 1, right? I would get 1, 1 is 0 with a carry, 0 with a carry, 0 with a carry, and I would put that with no carry over here. So to calculate the 2's complement of negative 8, we get the exact same bit pattern, all right? Now, that can't be true, all right? So this has already failed. All right, but let's see what happens with our overflow bits and our logic that we've been talking about. So if you flip the bits and add 1 of this subtrahend, you're going to get the same exact bit pattern here, which should be your clue, like I just said, is wrong. So let's go 0, 0, 0, 1. Geez, I'm thinking ahead here in my brain. And then we're going to add, flip the bits, add 1, and then we're going to add these. Now, you learn this in other assembly language programming classes. But technically, this is wrong in certain circumstances, and this is one of them. What do I get? If I add 1 plus 0, I get 1 with no carry, 0, no carry, 0, no carry. I get 1 with no carry. What do I get here? If I treat this as a signed operation, no signed overflow. This is wrong, simply because we got the wrong answer. What is this number? Well, if it's a signed value, as it would be in the case, this actually is negative 7. You can work that out. I'll leave that as a test to the student. So when is 1 minus a negative 8 equal to negative 7? Never. Okay. So we do this math. If you add the 1 here, and you do this, it will not report the overflow correctly. You'll get the wrong answer and you won't know. This is why you don't do it. Let's look at it if we do it the right way to confirm that I'm not kidding, right? So if we do this the right way, we just flip the bits, we do the 1's complement, you set the LSB here. 1 plus 1 plus 1 is what? That's 1 with a carry, 0 with a carry, 0 with a carry, 1 with no carry, We get the same answer, which is why some people teach you to do it this method. However, look what happens over here. We have the correct status by looking at the fact that the carry into the MSB is not equal to the carry coming out of the MSB. This is why it's absolutely critical that you do not do it the wrong way. You don't flip the bits, add one, then do the addition. You flip the bits and you add one while you're doing the addition all at the same time in order to get the right answer. So I hope these examples clarified a few things about how to specifically do your additions, your subtractions, and how to interpret the results, whether they're signed or unsigned, and dealing with the overflows. So thanks for watching. See you next time.